In this lecture, we will discuss about the stationary states and non-stationary states. So, first of all, why we are interested in the stationary states and what are exactly the stationary states. So, we are interested in this because we are going to develop the time-independent perturbation theory, the variational method, the WKB approximation methods, and these three methods, the approximation methods, works only for the stationary states. So before going deep into the approximation method itself, I just want you to just refresh your memory about the stationary states. I know that you must have learnt about them, but just to refresh your memory, let's just do some calculation for stationary states. So first of all, what are stationary states? So these are those states which can be written as the product of two functions. One is the function of space only, and the second is the function of time only. So if we can write the state that we are interested in this particular form as the product of these two functions, then that state in quantum mechanics is called the stationary state. Now it has very interesting consequences, and I will show you what the consequences it has. We will do a very simple calculation and we'll see why these states are called stationary states, right? So as we know that to just get this particular wave function, we need to solve the Schrodinger equation. In general, the time-dependent Schrodinger equation. So let me just write it for one-dimensional motion. The Schrodinger equation, time-dependent Schrodinger equation can be written as this. So it is just the double derivative, the space derivative of the wave function, which is the function of x and t, because I am talking about the one-dimensional motion only. And one more thing that we are interested in, and we are assuming that the potential of the problem is just the function of space, right? It is not the function of time, and we are just dealing with the problems where the potential is not changing with time. Then so this is the time dependent perturbation, time dependent Schrodinger equation, which you need to solve to get this particular state. But what if we restrict ourselves to just get these solutions which can be represented in this form, so which are variable separable solutions, right? So if we just want to calculate the variable separable solutions, what will happen to the Schrodinger equation, the time dependent Schrodinger equation, just put this value of psi of x and t in this place and just see the consequence. So it will be psi of x and phi of t, v of x into psi of x into phi of t, which is equal to iota h cross del by del t of psi of x and phi of t. It is also the partial derivative, right? But now because this differential is just with respect to the space coordinates, so that time dependent function can be taken out of this particular derivative or differential coefficient. So the equation will be like this. This phi of t will be out of the derivative, and this partial derivative will be converted into the complete differential coefficient. So it is just second derivative of phi of x, which is plus v of x into psi of x into phi of t. Now on the right hand side, the differentiation is with respect to time coordinates. So the function which depends on just space coordinate can be taken out. So it is phi of x into, then again this partial derivative will be converted into the complete derivative. and it is d over dt of phi of t. Just do a little bit more algebra to that. So just divide the whole equation by the product of phi of x and sorry, psi of x and phi of t. So when you will divide this particular term from by just psi of x and phi of t, the phi of t will cancel out, and this will be h square h cross square over 2m 1 over psi of x, and second derivative of psi of x. In the second term, these two terms will cancel out and they will be just v of x. On the right hand side, this psi of x will get cancelled out, and it will be iota h cross 1 over phi of t into d over dt of phi of t. Now this equation is interesting equation. Why? Because on the left hand side you have just all the functions which are of the function of x only, the space coordinate, and on the right hand side there is just the time dependent functions. Now this part, the left hand side, is the function of space coordinate, which is equal to the function of time coordinate, which can only be true when these two functions are individually equal to some constant, right? So it is just constant. We are assuming the constant as e. So this uh, is very important when on the one side all the functions are of some particular variable, and on the other side the other functions are of different variable, then that can only happen when these two sides are equal to some constant, and in this case we are assuming that constant to be e, and later I will explain you why that constant is e. We are assuming that constant to be e. So just by doing so, the left hand side will be 1 over psi of x, second derivative of psi of x plus v of x, which will be equal to e, the constant. And this equation can be converted into very familiar equation, which is the time independent Schrodinger equation, just by multiplying this equation by psi of x. So this will be h square over 2m. This will get cancelled out and it will be just second derivative of psi of x plus v of x into psi of x is equal to e into psi of x. So this is the time independent Schrodinger equation, and we could be able to get that equation just by putting this variable separable solutions, which are the stationary state, into the time dependent Schrodinger equation, which is very important and interesting to note down. So that is just if we equate this left hand side to the constant e, we will get this time independent Schrodinger equation. Time independent Schrodinger equation. We can only solve this Schrodinger equation, the time independent Schrodinger equation, when we know this time independent potential. So if we know time independent potential, then we can solve this Schrodinger equation, and we can get the solution, which is psi of x, right, which is just the function of space only, which is this part of this the stationary state solutions. So this is just when we equate this left hand side, right? What will happen when we will equate the right hand side of this equation? So the right hand side is iota h cross 1 over phi of t into d of d phi of t by dt. So if we equate it with the constant e, because we have assumed that both the side has to be equal to some constant e. This is a constant. So just rearrange this and just do basic calculus. So it will be there, and this will be minus iota over h cross, and you can just integrate these two sides and you will get phi of t as some constant, which I'm not writing it here, but there will be some constant, and e to the power iota e t over h cross. So this will be the solution of this equation, right? So all these things are the consequence of this particular state, which is the stationary state. When you will assume that the you are solving Schrodinger equation, time dependent Schrodinger equation for the stationary states only, which are the state which can be written in this particular form, then the one thing that you will get is to solve the time independent Schrodinger equation for to get this the first part of the separable solution, the stationary state, and the second part will always be in this form, which is exponential of minus iota et over h cross. So this will always be in this form. So uh, we can write this stationary state in this form. So we can write these stationary states as this function, which is just the function of space, which we will get from the time independent Schrodinger equation, right, which we can only solve when we have the potential. So let me write it again. So if you know this potential, then you can solve this differential equation. And after solving this differential equation for this particular potential, you will get this part of the stationary state. And this second part is always this particular function, which is exponential of minus et over h cross. So the stationary states are those states which can always be written in this particular form. The first part has to be calculated from the time independent Schrodinger equation, and the second part will always be in this form, right? You just have to remember it, cram it, so that you can write it there. But this is the way you can derive it. So this is the consequence just of putting this stationary state in the time dependent Schrodinger equation. So this is what we get, right? So let me just show you why these states are called stationary states. Now the basic physics behind it. Now this is the form of stationary state. So stationary states will always be in this form. Now, now if you want to calculate the probability density for this particular state, so the probability density is the square of the mode of psi of x and t, right? So, and we know that this is the complex function, and we can write it as the complex conjugate of psi of x and t into psi of x and t, right? The complex conjugate of this particular function will be the complex conjugate of this spatial part and the complex conjugate of this exponential part, which is when you have some already complex function, then just you just have to replace, you just have to change the sign of in front of iota. That will be the complex conjugate of this particular complex number. So here it is negative, so it will be positive iota et over h cross, which is the conjugate of this particular function, right? and you just have to multiply it with this state, the stationary state. So it is minus iota e t over h cross. And as you know that these are just ordinary functions, ordinary complex functions. So it can be written as the psi, complex conjugate of psi into psi of x. And when you will just multiply these two exponential functions, right? So they will add. So it will be iota e t over h cross plus, sorry, minus iota e t over h cross. So it will be 0. So it is psi star, which is the complex conjugate into the psi of x, and e to the power 0, which is 1, right? And it will be psi star and psi, which can be written as the mode of psi square. So the interesting result we get is the probability density of the stationary state, or in the stationary state of some particle, which has to be written like this, and it came that for stationary state it is just this, which is just the function of space, and it is time independent. And that's why, that is the reason these states are called stationary states, because if the particle is in this kind of state, then their probability density will always be time independent. The probability density will not change with time. Of course, the state will change with time because it has this particular part, but the probability density of finding particle in some space will not change, right? Not only that, if you calculate the expectation value for some operator, so let us suppose that there is some operator q, which is the function of x operator and the momentum operator, right? So if you just want to calculate the expectation value for this stationary state of some quantity, it may be the position, it may be the linear momentum, angular momentum, or energy. So just calculate the expectation value of some operator q, which will be psi of x and t acting, sorry, into the scalar product with q of t, which is acting on psi of x and t. I know that you all have heard about them, how to calculate the expectation values in the first unit. And in integral form, it will be psi star of x and t, q dash acting on psi of x and t into some volume element, right? The complex conjugate of this particular state, sorry, this particular state will again be the complex conjugate of this part, and we will just change the sign of the second part. So it will be psi star of x into e to the power plus iota et over h cross, and q q cap into psi of x into e to the power minus iota et over h cross d tau. Again, when you multiply these two parts, the time dependent part will cancel out, and the expectation value of any operator, right, which will be psi of psi star of x into q bar into psi of x data. And again, this is just the function of space coordinate, and it is again independent of time. So the interesting part in this particular lecture is that when you are dealing with the stationary states, first the stationary state will or can always be written in this particular form, right, as the product of two functions. One is the function of space and second is the function of time. And after doing some mathematics, just putting this particular state in the time dependent time dependent Schrodinger equation, you have calculated the time dependent part will always be in this form, the exponential of this particular quantity into the spatial part, and this spatial part can always be calculated by using time independent Schrodinger equation, right? And after doing that, we have calculated the probability density for these stationary states, and we have shown that the probability density of finding the particle at some place in space is time independent, right? So that probability density is not changing with time. Also, we have calculated for stationary states the expectation value for any operator is also independent of time. So these are very important properties of stationary states, and these are the states for which we are going to develop the approximation methods first, right? One more thing you have noticed is that when initially we were putting this particular state in the time dependent Schrodinger equation, we have assumed that the potential, which was the function of time, space and time, we have assumed that to be just the function of space only. So that is also very important. One more thing, the Hamiltonian of any system is generally, if you are just writing it, just the operator part, right? So it is like this. Yes. So the Hamiltonian for any system is this for any quantum system, and it is time independent if the potential of the system is time independent. So as I said in the previous lecture that the stationary states are for the time independent Hamiltonian. So that is because for the stationary states we assume that the potential is time independent, and if potential is time independent, the whole Hamiltonian is time independent. So the summary of this lecture is that uh, these stationary states are very interesting states, right? Because for these particular states, the probability density will be time independent. They can be written in this particular form, and we can just convert the time dependent Schrodinger equation into time independent Schrodinger equation, which we can solve for to get this spatial part. So this is what the stationary states are, and these are very interesting states. Again, I have said many times, you already have studied about the stationary states. It is just to refresh your memory, right? So in the next lecture, we will discuss about the degeneracy and uh, degeneracy of energy levels, because that is another important concept which you have to know what is the meaning of degeneracy and about that particular concept. So thank you so much, and we will just meet in the next lecture. Thank you.